In this lesson, we are going to write a simple program to verify whether a given number n is prime or not. So what is a prime number? A prime number is a positive integer that can be divided by exactly two numbers, 1 and the number itself. So let us quickly see what all numbers can be called prime numbers. 1, and if we draw a set of all the numbers that can divide 1, we get only 1. 1 is not a prime number because for a number to be prime, it should be divided by exactly two numbers. 2 can be divided by 1 and 2. This is a prime number. 3 again can be divided by 1 and 3, so this is a prime number. 4 can be divided by 1, 2 and 4. This is not a prime number, and we can go on. So the smallest prime number is 2. So the simplest thing that we can do to verify whether a given number n is prime or not is to try dividing it by all the numbers greater than 1 and less than n. That is, for I starting 2 to n minus 1, if there exists any such I that divides n, then n is not prime. And if we can come out of this loop without finding any such I, then n is prime. And let us just assume that for the special case when n is less than or equal to 1, we handle it correctly in our actual program. Now a simple observation here is that there cannot be a factor of n other than n itself that can be greater than n by 2. So we cannot find a factor of n greater than n by 2 and less than or equal to n minus 1. So we do not need to run our loop all the way till n minus 1. Only a check till n by 2 should be sufficient. This sounds good, but can we do something better here? Let us see. If a divides n, then there must exist another number b that should be equal to n by a, and b should also divide n. So we should have a relationship like a into b is equal to n. A and b are called cofactors. So all the factors of n always exist in pairs, and it will be further clear if I use an example. So let's pick up a number 36 and try to see that what all pair of factors it has. So the first factor of 36 is 1, and if we say that a is equal to 1, then b must be equal to 36 by 1, which is 36. Next pair of cofactors would be 2, and 36 by 2 is 12. Sorry, it should be 18. 3 and 12, 4 and 9, 6, and 36 by 6 is 6. This is a special case where a is equal to b. Next factor is 9, and the corresponding cofactor is 4. 12 and 3, 18 and 2, and finally 36 and 1. If you carefully see, we can see a pattern here that the pairs are repeating. Only the order is different, but the numbers are the same. So we have a 9 4 and we have a 4 9, 12 3, 3 12, 18 2, 2 18, 36 1, 1 36. So we're getting the same pairs again. For a and b, there can be a case when a is equal to b, and that would happen only if n is a perfect square, and in this case this equation will translate to a square is equal to n, or a is equal to square root of n. In our example, 36 is a perfect square, so we are able to get such a pair of cofactors where a is equal to b. What if a is not equal to b? So if a, for example, is less than b, then if we see carefully, then a should always be less than square root of n, and b should be greater than square root of n. Similarly, if b is less than a, then b should be less than square root of n, and a should be greater than square root of n. So if a and b are not equal, one of them has to be less than square root of n, and another one has to be greater than square root of n. Let's try to plot all these cofactors on a number line, and this should be further clear to you. So I've drawn a number line here, and it is not so accurate, and we'll only try to approximate the position of the integers on this line. So let's pick up the first pair of factors. 1 should be somewhere here and 36 is here. 2 should be somewhere here and 18 somewhere midway between 0 and 36. 3 should be here and 12 somewhere here. 4 should be here and 9 should be somewhere here. So we can see that one of the numbers in the pair is less than square root of n and another is greater than square root of n. And of course we should also plot 6 and 6 where a and b are both equal to square root of n. Rest 4 cases are just repetitions of our previous first 4 pairs, and we have already plotted them. We have shown it for n is equal to 36, but this property is true for all values of n. So now we can say that, hey, if I do not get a factor of n all the way till square root of n, then I can clearly say that I will not be able to get a factor after square root of n as well. So all I need to do is check only till square root of n. So in my actual program, I do not need to run the loop till n by 2. We can run the loop till square root of n and that should be enough. Running the loop till square root of n is a lot more computationally efficient, and you can pick up some values of n and try to see that square root of n is a lot lesser than n by 2 for higher values of n. So this is the pseudocode. We'll leave the rest of the implementation to you. Take care of the special cases where n can be less than or equal to 1. In next lesson, we will discuss another algorithm for primality testing, which is a very famous algorithm called sieve of errata trees. So thanks for watching.